All right, well, hey, welcome to Math 105, and this is our first class of October, if you can believe it. We're just moving right along. But hopefully the quiz went well. Again, we'll talk about it later once everybody is done taking it and I have a chance to look at them and grade them. Um, but before we keep moving on with derivatives, I was just curious if there are any questions about the homework or anything we've talked about so far. All right, so hearing nothing, then I'm going to assume we're doing all right so far. So we're going to go ahead and continue our discussion about derivatives. So remember what derivatives are. Derivatives are rates of change. They're instantaneous rates of change in a function, which means that they're slopes of tangent lines of graphs. All right, so derivative is the rate of change, is the slope of a tangent line. And we found it by playing like well, one of the most famous math tricks in the world, which is basically I like to say fake it till you make it, right? We used 2 points and to make a line. Obviously 2 points doesn't mean it's a tangent line, so we basically just took those 2 points, brought them so close together that they were actually the same point, right? So mathematicians like to play those little tricks. Here we used limits to do that, right? So I'll remind you about that. But today we're going to talk about, derivatives. Do they always exist? What do they mean graphically? And then we're going to start developing rules. We're going to develop rules that are going to speed this process up. We started seeing that it was a little bit easier if we just did it the one time and left it as a function of x, right? Instead of trying to figure out the rates of change for a whole bunch of different points. But that process is still long when we use that difference quotient, right? And do the limits. And so what we're going to do today is, again, the mathematics kind of trick of, well, what if we just take this kind of function and apply the rule to it? Um, let's see what falls out. All right. And so basically over the next couple of days, we're going to be developing the real quick ways of getting the derivative so that we don't actually have to build those slope formulas and take the limits. All right. Anyway, so that's where we're going to be heading today. So let me go ahead and switch views here, and I'll meet you up at the whiteboard. All right. So let me just remind you what we were doing when we found the derivative. So first of all, if we have a function f of x, the derivative, we have a couple of different ways of representing it. One is like this, df dx, or if we want to think of it as dy dx, if we have y equals. Okay, so this is one notation for the derivative. But the other one is this guy f prime of x. Now, I'll just let you know that I primarily use the f prime. This is the one that I'm going to use the most to show you that we're doing a derivative. But both of these are equivalent. They both mean the same thing. And so you might be curious as to why do we have two different notations? Well, I don't know if you remember me telling you the story about calculus and how it was actually kind of invented independently by two different people. Well, this is one of the carryovers of that. We had Newton and we had Leibniz, right? Well, Newton wrote them with the little primes. Leibniz wrote it like the little fractions. And so those both kind of have carried over, and you'll see them both like a lot, kind of depending on the situation. So you need to get comfortable with both of them meaning exactly the same thing. Now, one nice thing about the Leibniz notation, like if you look at this guy right here, right, where it says dy dx, this helps you remember that what we're doing is actually finding a slope. Because slopes, remember, are change in y over a change in x, and that's exactly what this is saying. instead of using the delta, we use the little d to say that they're infinitesimally small steps, but it's still a slope. So that's one nice thing about the Leibniz notation, is that it helps you remember what you're actually doing. But the Newton notation is a little bit faster, a little bit easier. And so for someone lazy like me who doesn't like to write extra stuff, I'm a big fan of using this. Okay, so this guy, f prime of x, the definition, I just want you to recall that there were two different definitions for this. But when we were looking at it as a function, we used this one. The limit as h goes to 0 of f of x plus h minus f of x over h. So this is called the difference quotient, and it's just a slope. It's the change in y over the change in x. So think of this h as that step between the 2 points, and limit as h goes to 0 means we're bringing those 2 points closer together until they look like 1 point. All right, so just to help us kind of warm up, let's do one here. Let's see what we get when we differentiate a function. And we may have done this one. I don't remember if we did. I don't think we did. But if we did, I apologize. You're going to see it one more time. All right, so let's look at f of x equals 1 over x. So if we go to the definition, f prime of x is going to equal the limit as h goes to 0 of 1 over x plus h minus 1 over x divided by h. So notice that all I'm doing is I'm taking x plus h and I'm putting it into this function. And then I'm subtracting the function. And then I'm dividing that all by h. And that's always the process, no matter what the function is. So if you go back and you look at your notes from last time, you'll see that we did a bunch of these. Square root of x squared, sine of x, it doesn't really matter. We always start by plugging in x plus h, subtracting the original function and dividing by h, and then do our fun limit stuff. So for this one, since it's fractions, what we're going to do is we're going to multiply top and bottom by x and x plus h. So that's going to eliminate the fractions on top. So we get the limit as h goes to 0 of x minus x plus h all over h times x plus h. We can subtract up top and we end up with a negative h over hx times x plus h. The h's cancel. So we've got a limit as h goes to 0 of negative 1 over x times x plus h. And now when we put 0 in for h, we end up with negative 1 over x squared. So that's the derivative of 1 over x. If f of x is 1 over x, then f prime of x is minus 1 over x squared. And now we've got the slope anywhere. Slope of the tangent line at any point. So choose your favorite value, plug it in, and you'll get the slope of the tangent line. All right, so we did a ton of this last time. Yay, great. We've got a process. And so now if we want these instantaneous rates of change, so an instantaneous speed or anything like that, we got it. Always the same process. Always the same process. It's a recipe. Okay, so before we go too far into this, maybe one of the questions we should answer is, does the derivative always exist? Can you always do this with any function? Right? Now, that may feel like a weird question to ask, because so many other times when we have operations and things that we're doing, of course it always works. But there are times when they don't. A good example is think about inverses. Not all functions have inverses. There are certain properties that the function have to have in order to have an inverse. right? Primarily, they have to be 1 to 1. Okay, so there are some things that are restrictive. There are others that aren't. And the derivative is one of those things that is restrictive. You can't always take a derivative. It's not always possible. Okay, so let's talk about that. Let's talk about where does this fail to exist. All right, so where does this guy fail to exist? All right, now, something like 1 over x, you saw we could differentiate it. But there were still actually problems with 1 over x when it comes to the derivative existing. And in fact, you could probably tell me, where is there a problem with this derivative? Can you tell me an x value where we might have an issue with the derivative there?
0.
Yeah, how about 0? Why is 0 a problem?
It'll be undefined.
Yeah, we're dividing by 0, which is undefined. So even something like that, well, yeah, we can differentiate it, but there are times where the derivative doesn't even exist. And I actually just said a word, and I don't know if I told you guys this. I just said we differentiated. Differentiation is the process of taking a derivative. Let me write this up because I know sometimes mathematicians, we have a tendency to have all kinds of words that are related, but we don't always explain them. And I want to make sure you guys know exactly what I'm talking about because I don't want the language to be the issue. All right. But differentiation this is the process of finding a derivative. And so you can take a derivative. You can find a derivative. Okay, those are interchangeable. But you can also differentiate a function. Okay, so if you ever hear me say differentiate, means take a derivative. Differentiation, the product of finding a derivative. A function is differentiable if its derivative exists. Okay, so all the different variations on that word differentiation, they're all derivatives. Okay, so because I think what I said something was like, we can differentiate a function, right? Like we were able to differentiate 1 over x. We were able to find a derivative. However, there were still problem spots. Like there was a problem at 0. Okay, so let's talk about where this fails to exist. All right, so here are some places where we're going to have issues with the derivative. The first is with discontinuities. See, I told you we'd talk about continuities later. Right? Continuity still matters. Because if a function is discontinuous, then it's not differentiable there. The derivative doesn't exist. And I want you to think about why, right? When we're finding a derivative, we're finding a slope of the tangent line, we're finding an instantaneous rate of change. Imagine we've got a discontinuity. And we'll even talk about like the different types of discontinuities. But for example, what if we've got, say, like a jump, one of those kind of jump discontinuities? And that's happening right here at, call that guy C. And I were to ask you, what is the derivative at C? What is the slope of the tangent line at C? Well, think about how we define the derivative. Right? We're going to be at C, and we're going to take a little tiny step. And then we're going to make that step get smaller and smaller and smaller. Well, if we were to evaluate this function at C, that's this point. And then I take some other point that's a little step away. Remember, H is your little step away. So we're over here. And I connect those two. Does that look like a tangent line? No, obviously not, right? Clearly, that's not a tangent line. And it doesn't matter how close I bring this thing, still going to run into the same problem. Okay, but then you might go, well, but what if we were actually like approaching from the other side? Right? That's starting to look like a tangent line. And that's true. But the problem is for a derivative, we have to be able to be doing this on both sides. It's kind of like a limit. Remember when we did the limits, it had to be both sides. We had to be approaching the same value. Same thing has to happen for a derivative. And that should kind of make sense because a derivative is a limit, right? It's a special limit. We're evaluating that slope, but it's still a limit. Limits are two-sided, so derivatives are two-sided. So we got to get the same thing from both sides. Okay, so you can see why a jump is a problem. If there's just a hole, well, this is awfully hard to actually find a slope of when there is no point. All right, so obviously there's got to be a point there. Well, if there's got to be a point, then you can see also why infinite limits are a problem, right? Something like that. Because there is no point at this asymptote, so trying to find the slope at that point is impossible. Okay, so that's the first problem with differentiation, is that if you ever have a discontinuity, you're not going to be able to differentiate. You're just not, the function's not differentiable there. Okay, so continuity. Got to have continuity, it's got to be continuous for a function to be differentiable. However, just because it is continuous isn't enough. All right. So there are some other problems, and this next problem, I call it a kink. So I say it's a kink in the graph. Other people will say it's like a really sharp turn or something like that. Now, obviously, when I use a word like kink, that's not a very good mathematical definition. Let me show you an example so you know what I mean when I say a kink or a sharp turn. And this is a function you know very well, absolute value of x. Okay, look at the absolute value of x. So that's the v, look something like this. And I specifically want to know, what about the derivative at 0? So what about at this point right there? All right, so first things first, it is continuous, right? Clearly it's a continuous graph. But there is that real sharp turn. So let's talk about why that sharp turn is a problem. So let's think about tangent lines. Let's think about rates of change. And again, approach it from either side. Like let's say we're coming from the left-hand side. The tangent line is actually the line itself. And this line has a slope of -1. So over here on the left-hand side, the derivative is -1. Always -1 over there. On the other side, again, the tangent line is that line, and this one has a slope of 1. Okay, so now maybe you can start seeing the problem. On one side, the slope is -1. On the other side, the slope is 1. We're not getting the same value. The same kind of issue. The limit doesn't exist as we're going to 0, because on one side we're getting 1, and the other side we're getting -1. Okay, so this is a kink. It's a really sharp turn in the graph. And the other way to think about it is, okay, does tangent line at this point even make sense? I mean, there's all kinds of lines that never really quite cross it. But think about this. If we are drawing if we were paying attention to our tangent line, we just keep putting it on the graph as we're going. Once we hit 0, there has to be an immediate flip to this other one, right? It's not a nice smooth transition. We don't get to just go, oh, here we're at -1, and then we slowly make our way to +1. No, we're at -1, and then instantaneously it flips. If that ever happens, that's a problem with the derivative. Okay, so the derivative doesn't exist there. The function is not differentiable at that point. Other people will call this like a cusp in the graph. Sometimes you'll see it even if you've got like a curvy graph, like this one I know is really just like it's linear. The V is very linear. But you would run into the same problem if you had a graph that say looked like this. Right, so let's think about this one. So we've got, oh, nice tangent lines, no big deal. They're slowly turning, slowly changing, slowly changing. And I get here, and then I immediately have to flip over to the other direction. So this point right here has the same issue. Locally, there's a real sharp turn, looks like a V. Okay, so that's another place where you have problems with differentiation. So just because you're continuous, not good enough. There are plenty of continuous functions who are not differentiable at points. All right, so we got to watch out for kinks in the graph. Here's another problem spot, are where we get vertical tangent lines. An example of this, a really good example, is the function cube root of x. If you were to draw the graph of cube root of x, I'll do my best here. Kind of looks like a square root, it's a little bit sharper. But then we also, on the other side down here, get exactly the same thing. So this is f of x equals the cube root of x. And kind of follow the tangent line. So down here, we've got a positive slope. It's getting a little bit bigger, steeper, 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 until eventually it's straight up and down. Well, I don't know if you remember, but when you have a vertical line, the slope doesn't exist. Or sometimes we'll call it an infinite slope. Okay, but the slope doesn't exist. Well, if the slope of a vertical line doesn't exist, then the derivative can't exist, since the derivative is the slope of that line. And then as soon as we get past that, okay, it's no longer vertical, so we have a slope, it's positive, it's getting smaller as we go, but it exists everywhere except for this one spot where we have a vertical tangent. Okay, so again, a continuous function. I can draw it without lifting my pencil, but there is a place where differentiability is an issue. Okay, so vertical tangent lines, and this is solely because the slope is undefined. Slope doesn't make sense for a vertical line. All right, so vertical tangent lines, and there are a few other weird things. Okay, there are a few other weird things. We're not going to talk about all the various weird possible things that could occur. These are the main ones. These are the ones that we see way more frequently. Okay, so if you ever have a graph that has a discontinuity, a kink, or a vertical tangent line, those are going to be places where you cannot differentiate, where the derivative is not going to exist. All right, so yay. This is kind of nice though, because we can look at graphs and now have a sense of what's happening. The other thing that is sometimes useful is to actually take the graph of a function and be able to sort of determine the derivative, see what the derivative function looks like, just by thinking about the slopes of the tangent line. Like you can get a really good picture of a derivative just by paying attention to slope values. All right, so let me show you an example. Actually, before I go there, any questions on this? Does that make sense why these are problems, Bob? All right.
Quick question. The sharp turn, that means that it's only turning at one specific point, right?
Correct. It's at one, yeah. So when we're at that one point, there's like an immediate change in direction.
Great. Okay, thank you.
You're welcome. All right. Well, let me show you this. This is actually kind of handy. Let me show you how you can graph a derivative. By looking at the graph of the function. And I think the best way to do this is actually just to show you an example and talk it out as we go. So let me put on a function here. And I'm not going to give you an equation. If you have an equation for the function, we know we can find its derivative by using that limit definition, right? But suppose that you don't have an equation for this function. So here is a function. And what I want to do is I want to graph its derivative. So we'll call this guy f of x. Now what I want down here, and I'm going to try to graph it pretty much right under it. We're going to draw a graph of f prime. Okay, so here's where it's really important to remember what the derivative is telling us. The derivative is giving us the slope of the tangent line. So if I were to draw a tangent line to this graph, let me just put one on here. All right, so there's a tangent line at this point. I can calculate its slope. I can get a number for this, right? The slope is a number. So what I'm going to do when I graph the derivative is I'm going to put that number as my y. So whatever that slope is, that's the number I'm going to use. Okay, so first, let's just get a feel for what's happening to the values of this derivative as we're moving along. So I'm going to start over here on the left as far as I can. And what can you tell me about this slope? Can you tell me anything about it? All right, so how about the fact Aries just put in there in the chat box? It's positive. Awesome. Yeah, it's going to be a positive number. And how do you know that it's positive? Yeah, so it's going upward, right? When we go up to the right, this is a positive slope line. If it goes down to the right, it's negative slope. All right, so we know that it's positive. How big is it? Well, I don't know. I can tell you it's bigger than 1. And the way I know that is a slope of 1. That's your good old pi over 4. I was about to say 45 degrees. So it's, pi over 4. So it's 45 degrees. So this one's steeper than that. So it's bigger than 1. But it's definitely positive. Now, let's just kind of move along for a little bit. So you notice what I'm doing is I'm just taking my pen, I'm using it to approximate the tangent lines, and I'm just kind of moving along the graph. Now, once we get here, what's happened to my slope? Still positive? Yeah, it's still positive, right? It's still going up. But how does this slope compare to the slope we started with? All right, so Eric says it's closer to 1, and that's probably true, but for sure it's smaller. This line is flatter than it was before, right? We were steeper here, we're getting flatter. That means the value of the slope is going down. And as we continue, it gets flatter and flatter and flatter, which means that slope is getting less and less and less. And then we reach this point right here. What can you tell me about the slope right here? Good. Fenrir just put in, it's 0. The slope is 0 because it's a horizontal line. So think about what happened. We had positive numbers, and they got smaller until they reached 0. So here's what I'm going to do. I'm going to start drawing the derivative on this set of axes. And let me just translate some points. So here was that point where it got flat. Okay, so that was this x value. Well, the slope of that tangent line is 0. So at that point, I'm going to draw a dot on the axis because that's a y of 0, so that's a slope of 0. All right, so we started over here. Let's just draw this guy. And what we knew was that this had a positive slope. Now, I don't know exactly what it is, but it's positive, so I'm going to give it this value right here. I don't have any scale on here, so I can just kind of wing it. If I had some scaling, I could do a better approximation. You remember doing that in homework by 2.1, where you're trying to approximate the instantaneous rate of change, and so you use the slope and you made a guess using the rise over run. Well, you could do the same thing here, but I'm just going to go with it's a positive value. But what I do know is as I'm moving, I have to get positive numbers, but they have to get smaller. So the derivative is going to look like this in this interval. I have positive slopes. I still have positive slopes. I still have positive slopes. Because remember, these are positive numbers. They're just getting smaller until eventually I hit 0. Okay, well, now let's kind of continue. Let's see what happens next. So we had reached this point where we were flat. Now, once I get past that peak, and I move over here, what just happened to my derivative? What happened to my slope? What's different now?
It's negative now.
Now it's negative, right? It's going down. So all of a sudden, we went from positive slopes to negative slopes. And they're going to stay negative, but they start getting more negative because it's getting steeper, right? And then eventually, it starts getting less steep. And as I keep going, then I run into where it's flat again. So let me mark a couple of points. I'm going to mark this point where we flattened out. But I'm also going to mark this point where we switched from getting steeper to getting flatter. Right? So that point right about there is where this thing goes from being steeper to being flatter. So let me put that one in here as well, because that's kind of an important point. So when we got to this bottom, we were horizontal, which meant our slope was 0. So I'm going to put 0 on my graphic. Now, in between these 2 points, I'm decreasing, so I need negative numbers, but I need my biggest negative to happen on this dashed line. So I'm going to make it look like this. Okay, where this value, this y value is the slope. It's a negative slope, and it's that steepest slope right there. All right, so let's see what happens now. So at this point, we start moving, we go back to positive. We stay positive, we stay positive, we stay positive until it flattens out again. So let's mark this one, because that's where we flatten out. And then just like over here, there's a point where we go from getting steeper to getting flatter, right? The line is getting steeper, 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 then starts going flatter, flatter, flatter. So again, I don't know exactly where it is, but it's probably like right about there. So let's mark that again, kind of important. And that's going to be the greatest slope. So we'll have some slope value there, and it does something like this. And then once we get past this peak, notice that we just start going down, and it gets steeper and steeper and steeper. That means our slope needs to be more and more negative. So it does something like that. So whatever this function is, if I were to differentiate it, the derivative would look like this red graph. Approximately, right? This isn't necessarily a really good picture of the derivative, but at least it's getting the idea of what the derivative looks like. So let me kind of just write down the steps I use to try to do this, to try to draw the derivative, because there were some very specific points that I picked. All right. So here's what I look for. I find all places, so all points with a horizontal tangent line. And those are really easy to spot, because those have to be places, again, I'd literally use my pen. So use your pen, use your pencil, use anything you've got that's straight. I literally use that to be my tangent line. And you see me kind of move this along the graph. This is what I do, literally, if I'm going to do this myself, okay? But it's really easy to see then, oh, I just got flat. Oh, there's another place I'm flat. There's another place I'm flat, and so on, right? So I look for places with a horizontal tangent line, because I know what this is. These are going to be x-intercepts on the graph of the derivative. Because horizontal lines have a slope of 0. So if what we're plotting are slope values, that means we need to have zeros there. Those are x-intercepts. So the very first thing I would draw if I was doing this would have been these 3 points. Those are the 3 places where I flatten out. Okay, so find all those points with horizontal tangent line. The other thing that I do is I look at, are we going up or going down? So between these points, I'm just going to put here, are we going up or down? So for example, look at these two, right? Those are 2 of the places where we got zeros. And in between there, I'm going up. So what this tells me is that if we're going up, my graph is going to be above the x-axis. So what I'm writing in red is derivative stuff. So if we're going up, our derivative is above the x-axis. If we're going down, the graph is below. So look at what we drew for our graph of the derivative. Look at the places where we were going up. We were going up at the start, and we went down, and then we went up again. But those places where we were going up on my graph of the derivative, I'm above the y-axis, right? I'm above the y-axis between these 2 points. I'm above the y-axis over here. And then where I was going down, so in this region and over here, the graph of my derivative was below the x-axis. So right down here, I'm below the x-axis, and then I was below the x-axis again. Okay, and then the last thing I do, and I apologize, I should have started this up a little bit higher so I could have written the number 3. But the third thing that I look at, I'll run it up here. Once I do this, then I look for, I find the places in between the horizontal tangent lines where the slope is greatest, or where the line is steepest. So again, come back to in between these two where we were increasing. Right, here's my tangent line. It's getting steeper, it's getting steeper, it's getting steeper. Then it starts getting flatter, right? Steeper, flatter. Same thing where I was coming down. Getting steeper, steeper, steeper. Oh, now I'm starting to get flatter. So I find those points where the tangent line is steepest. So that would have been these 2 points. And notice what happened on the graph of our derivative at those 2 points. That's where we turned around. That's where we turned around to come back to 0, right? It's going down and then back to 0. Going up, back to 0. So those correspond to, these are the turnaround points. On the derivative graph. Yeah, so those are the things that I look for to help me draw the graph of the derivatives. It's just a matter of watching for those things and then kind of piecing it together. So you'll probably have a couple of these on your homework and stuff, and at first it'll feel uncomfortable, but the more you practice it and kind of follow my recipe, the easier it's going to be. But notice that I don't need to have an equation for the derivative to have an idea of what, or of the function, to have an idea of what the derivative actually looks like. And that's kind of the power here, is that we're not going to be restricted to having an equation. All right, so there's the derivative, at least how it, graphically what's going on. Okay, so I want to share one more thing before we talk about the rules. Normally, I wouldn't talk about this until later, but this book introduces a little bit earlier, and just in case there are homework questions on it, I want to make sure you know what they mean. Okay, so I'm going to do things slightly out of order what I would do. But what I want to show you are what we call higher order derivatives. All right, so, but real quick before we jump off that, questions on this? If you're at a point where you can formulate them. I know sometimes you got to see this a couple times, play with it. Okay, so then let me just introduce you real quick to these higher order derivatives. They're not as complicated as they might seem, but just so you know them when you see them. Okay, so what these are, higher order derivatives, we call them, say, the second derivative. You could have a third derivative. You could have a fourth derivative. And so on and so forth. There's a fifth derivative, sixth derivative, seventh derivative, blah, blah, blah. So what we'll do generically is we'll write nth derivative. Now, before I talk about what they are, let me show you the notation. So you remember for the derivative, there were the two ways. There was the f prime, and the other was with the dy dx. Well, we have similar, for each one of these, we have a similar way of doing it. So for the second derivative, you will see either f, what we call double prime. It has two apostrophes. Or with that dy dx thing, we put 2's up there as powers. Okay. Now, both of those mean the second derivative. Real quick, because some of you may have caught this as you were writing it and maybe wondering, did I do something wrong? Did I make a mistake? No, this is definitely intentional. You notice that those 2's are in different places. Those powers, they're not exactly powers, but they kind of are. The first one is after the d, so it is between the d and the y. And the one on the bottom is after the x. That was intentional. That is the way that is written. Okay, so that's our second derivative. A third derivative. Well, now instead of 2 tick marks, apostrophes, this is going to have 3. So we call this f triple prime. And then I bet you can guess what happens with the Leibniz notation. We change those things to 3's. All right, so you see in the pattern. So if we go to the fourth derivative, obviously this thing with the Leibniz notation, instead of 3's, we're going to put 4's. But it's a little bit different with the primes because it gets to the point where we're going to have too many of those little tick marks and it's going to be hard to tell what they are. Once you get past the third derivative, we actually put the number in there as an exponent, but we put it in parentheses. That's what tells us it's a derivative and not a power. Okay, so this is the fourth derivative. So if we were to go to generic, you want the nth derivative. That's going to be f with the n in parentheses as a power. Or alternatively, if we're going to do the Leibniz notation, we just have n as an exponent. Okay, so this is the notation for our higher order derivatives. So then the question is, what the hell do those mean, right? Well, it's this easy. Second derivative just means after you differentiate for your first derivative, you take another derivative. You just differentiate it again. Okay. Oh, sorry about that, guys. Just suffered a bit of an earthquake. It was actually my dog. She just tripped over the cord. All right. So the second derivative is the derivative of the derivative. The third derivative is the derivative of the derivative of the derivative. The fourth derivative, the derivative of the derivative of the derivative of the derivative. Okay, so we're not doing anything new. We're just taking the function that became, that came from our derivative, and we differentiate it again and again and again and again, as many times as this tells us what to do. Okay, so if you ever run into that, it just means repeat the process. All right, So all of these are just derivatives of derivatives.
So what would an antiderivative be then? Or is that,
So antiderivatives, we'll see those later. But think about what anti means, right? That prefix, anti,
not a derivative?
means like against or opposite, right? Like if you're pro, you're for something. If you're anti, you're against it, right? So an antiderivative is just doing a derivative backwards. It's like instead of starting with the function and getting its derivative, antiderivative is start with the derivative and go back to the function. So it's just the opposite order. We'll get there. We'll get there. We got to make sure we have derivatives down and we understand them well before we can try to do antiderivatives. But that's what that means if you've ever seen that word. All right, so you know what, let me actually show you. We'll do one. We'll do a second derivative of a fairly nice function, just so you can see how this works. Now, we are going to have to do it with the limit definition because we don't have the rules yet. This is why I don't usually do higher order derivatives until we have the rules, because it's a lot. It can take a lot of time. But let's go easy. Let's just go with x squared. We all know x squared. X squared is a beautiful function. We love it. Let's see what happens when we differentiate it more than once. Okay, so for f of x equals x squared, question is, what is f prime of x? I think actually we did this one, but if not, let's just bang it out real quick. So this is the limit as h goes to 0, x plus h squared minus x squared over h. Remember, it's the same form, always. Always, 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 always. Plug x plus h into your function, subtract the original function, and divide by h. Now, I'm going to do this one kind of quickly. I'm not going to show you the algebra steps. So you're just going to either have to trust me or go back and look at them. But this becomes the limit as h goes to 0 of 2x plus h, which is 2x. All right, so if f of x is x squared, then we know that f prime of x is 2x. So we just found a first derivative. All right, so we already knew how to do that. Now let's get the second derivative. So for the second derivative, that just means differentiate the derivative. Differentiate what we just found. So we're going to do the same thing where we're going to plug in x plus h. Subtract the original function and then divide by h. So notice what we're doing is we're just differentiating the derivative, hence second derivative. All right, well, if you distribute everything in here, you get the limit as h goes to 0 of 2h over h. Since the x's cancel, here the h's reduce. So all we're left with is 2. So the second derivative of this function is 2. If you wanted the third derivative, we would just differentiate the second derivative. Once we have that, if we want the fourth derivative, we would differentiate it, and so on and so forth. So higher order derivatives are just do it again, and do it again, and do it again, do it again, and do it again, until you've gone as far as you need to go, as far as you've been requested to go.
So Bruce, I have a question.
Yeah, go for it.
In the homework, I think it's 3.2, it asks for the velocity and then it also asks for acceleration. would you
Yep.
just take a second derivative to find the acceleration since it's meters per second squared?
Okay, so you are like a half step ahead of me, Tim, because I was just about to tell you why we care about higher order derivatives, right? Like, what do they actually do? What do they mean? Why do we care, right? And that's actually a really, really good example. Velocity, we already saw that velocity comes from the derivative, right? In fact, that's why the derivative was even created, is to try to answer those questions about velocity. And so velocity is a change in position with time. Okay, well, if you look at how velocity changes, if you look at the change in velocity with time, that's called acceleration. And so acceleration is the derivative of velocity. But if velocity is the derivative of a position, then acceleration is the second derivative. So that's probably the biggest out there. And when I say out there, I mean not math. Math, we have all kinds of uses for the second derivative that we'll see. But out in the quote unquote real world, acceleration is one of the primary examples of second derivatives. So suppose that f of x, this is the position of an object, or maybe we'll call it f of t, let's say. So this is a position. This tells you where an object is at a given time. So like when we were talking about, tossing the pen up in the air, it's going to be a quadratic, right? It's going to be a sad parabola, so negative something t squared. Okay, so that's our position. So then the derivative, this is the velocity. We already knew that. But then the second derivative is acceleration. And you're probably used to that word, acceleration, for something to accelerate. And acceleration is just the change in velocity, right? Think about when we talk about acceleration, we primarily think about like cars and stuff, right? And that probably what comes to mind is speeding up, right? When you accelerate, you're speeding up. Well, speeding up means your speed is increasing, your velocity is increasing, your velocity is changing, so you're accelerating. I will tell you in the context of like physics, acceleration doesn't just mean speed up, it also means slow down. The common usage word that we use is decelerate. But in physics, it's still acceleration, it's just negative acceleration. It's a negative change in your velocity, it's slowing down. So when you're coming up to a stop sign, you are accelerating. You just have negative acceleration. Hopefully you don't have positive acceleration. That's bad news when you're coming up to a stop sign, right? But in the physics world, deceleration is negative acceleration. It turns out the third derivative has a name as well, the change in acceleration, the change in time. It's called jerk, right? Like a jerk something, that's a change of acceleration with respect to time. So that would be the third derivative. Beyond that, they don't really have use. But acceleration is a big deal. When you get to physics, I know a lot of you are probably going to start taking the calculus-based physics here coming up next quarter. If you're not planning on that, do it. Do it. It's a good class. It definitely shows you why we care about calculus, and it actually helps you understand calculus as well. But anyway, when you get there, you're going to learn about Newton's laws of motion. They're like the biggies. That's why anything does what they do. You know some of them, like the old, for a reaction, there's an equal and opposite reaction. That's the third law of motion. The first law is another one most people know. It's like a body at rest stays at rest. Body in motion stays in motion, right? That's the first one. But the second one is actually the important one. It says that acceleration is caused by forces. And so in physics, we actually start with accelerations. Accelerations are so big. So think about the second derivative then. We're really starting with second derivatives. And they matter. Now, once we get our rules down for differentiation, this will not be as hard as what we just did. because we had to do it the long way, right? But when we get the quick rules, which we'll develop next time, this will be fast. It's going to be super easy to get second derivatives or third derivatives or whatever derivatives, because we're not going to have to do the limit process every time. But unfortunately, we are out of time for today. It just flies by, right? So on Monday, we will get to those rules. We will speed this process up. We'll see how we can do things like this guy x squared. After Monday, is going to be like the easiest thing to differentiate. You're going to love it. You're going to be able to look at it and tell me what the derivative is. All right. So yeah, it has something to do with the exponent. You can definitely see that, like if you look at this, we started with an x squared, we went down to a single x, and then we went down to no x's. Yeah, that pattern definitely holds, right? So yes, there is the next one. The third derivative of this would be 0. But we'll see. We'll see where those come from, why that pattern exists. And we're going to do it with the definition. We're going to just use the definition of the derivative to kind of create these rules. And so you're going to see that there are nice rules for powers of x. There are nice rules for adding functions, for subtracting functions, when you have constants, and like we're going to have a whole big list. And those things are going to make it so that it's so much faster than using the limit rule. So that's our plan. That's what we're going to do on Monday. Also want to remind you, though, that the next homework set is due Monday night at midnight, so don't forget about that. Feel free to send me messages and stuff, and I'll be sure to be looking at them off and on over the weekend. But we'll also have a chance Monday morning to ask any questions on homework before we dive into the fast. Okay, so with that, I'm going to go ahead and stop our recording and wish you all a wonderful weekend.